Hello, and welcome to Science After Dark. Before we begin tonight's journey, take a moment to like the video and subscribe to the channel if you enjoy calm, thoughtful explorations of science and the universe. It really helps the channel grow and allows more people to discover these long-form scientific deep dives. And while you're here, I'd love to know something. Where in the world are you watching or listening from tonight? Let me know in the comments. Whether you're in a busy city apartment, a quiet house in the countryside, or somewhere on the other side of the planet entirely, there's something remarkable about that simple fact. Because wherever you are right now, every wall around you, every object near you, even the air you're breathing, is built from the very same thing. Atoms. Tiny structures so small that millions could fit across the width of a single human hair. And yet these unimaginably small pieces of matter obey some of the most elegant and mysterious physical laws in the universe. Tonight, we're going to explore the physics that governs atoms. Not just what atoms are, but why they behave the way they do. Why electrons don't simply collapse into the nucleus. Why matter is stable at all. Why atoms emit light in precise colours, combine to form molecules, and ultimately give rise to everything from stars and planets to living cells and human consciousness. The strange truth is that the world at the atomic scale does not behave the way our everyday experience might lead us to expect. Particles behave like waves. Energy comes in discrete packets. Certainty itself gives way to probability. And behind all of this lies a set of physical laws developed by some of the most brilliant minds in science. Some of the names you may recognize: Einstein, Bohr, Schrödinger, but others you may not. Mathematicians, experimentalists, and theorists whose work quietly reshaped our understanding of reality. Together, their discoveries revealed that atoms are not simple little balls of matter. They are dynamic quantum systems, governed by symmetry, probability, and the deep structure of the physical universe. Over the course of this video, we'll gradually peel back the layers of understanding that scientists have built over centuries. We'll move from the earliest ideas about indivisible matter through the discovery of electrons and atomic nuclei into the strange and beautiful world of quantum mechanics. Along the way, we'll explore the mathematical patterns hidden within atomic structure, the role of symmetry in shaping the laws of physics, and even the subtle effects of the quantum vacuum itself. By the end, we'll see how atoms are not just the building blocks of matter. They are windows into the deepest rules of nature. So wherever you're watching from tonight, settle in, relax, and let's begin our journey into one of the most fascinating subjects in all of science: the physics that governs atoms. Take a moment to notice the world around you. The chair you're sitting on, the device you're listening through, the walls of the room, the air moving quietly through your lungs. Everything you can touch, see, or feel appears solid and continuous. It feels stable, reliable, and familiar. Yet beneath that comforting surface lies a completely different reality. The ordinary objects of everyday life are not truly solid in the way our senses suggest. Instead, they are built from unimaginably small structures called atoms. These atoms are governed by physical laws that operate far beyond the limits of human perception. They're so small that if you lined up 10 million of them side by side, they would barely stretch across the width of a human hair. To picture their scale more clearly, imagine shrinking down until a single millimeter becomes an enormous distance. Within that millimeter would exist 1 million nanometers, and within just a few of those nanometers, entire atoms quietly exist and interact. A typical atom measures roughly 1/10 of a nanometer across, or about 1/10 billionth of a meter. At that scale, the familiar rules that describe falling apples, rolling balls, and orbiting planets begin to lose their usefulness. Atoms obey deeper rules that describe how energy can be stored, how particles move, and how probability itself becomes woven into the structure of matter. The idea that matter might be built from tiny indivisible units is far older than modern science. More than 2,000 years ago in ancient Greece, philosophers named Democritus and Leucippus began to speculate about the nature of matter. They proposed that if you continued dividing any object into smaller and smaller pieces, you would eventually reach a fundamental particle that could not be divided any further. Democritus called these particles atoms, from a Greek word meaning uncuttable. At the time, this idea was not based on experiments. It was a philosophical attempt to explain why materials behaved the way they did, why wood burned, why metals could be shaped, why smells could travel invisibly through the air. If matter consisted of tiny particles moving through empty space, many of these observations suddenly made sense. However, ancient Greek philosophers lacked the tools needed to test their ideas. There were no microscopes capable of seeing atoms. There were no instruments sensitive enough to measure molecular motion. For centuries, the atomic idea remained an interesting but unproven speculation. In fact, for much of history, many thinkers rejected the concept entirely. Aristotle, one of the most influential philosophers of ancient Greece, believed matter was continuous rather than composed of particles. Because Aristotle's ideas dominated scientific thought for many centuries, the concept of atoms faded quietly into the background. It would take more than 2,000 years before the atomic hypothesis would reappear with convincing evidence. By the early 1800s, scientists studying chemistry began noticing patterns that were difficult to explain without atoms. Substances reacted with one another in precise proportions. Water, for example, always formed when 2 parts hydrogen combined with 1 part oxygen. Carbon dioxide always formed when 1 carbon atom joined with 2 oxygen atoms. These regular patterns suggested that matter was not infinitely divisible, but instead built from specific combinations of smaller units. In 1803, an English chemist named John Dalton proposed the first modern scientific atomic theory. Dalton suggested that each chemical element consisted of its own type of atom, and that chemical reactions occurred when these atoms rearranged themselves into new combinations. Dalton could not see atoms directly, but his theory explained the observed behavior of matter with remarkable success. Gradually, the scientific community began to accept the idea that atoms were real physical objects. Even so, the early picture of atoms was still quite simple. They were imagined as tiny solid spheres, something like microscopic billiard balls. That model worked reasonably well for describing chemical reactions, but it did not yet reveal the deeper physical rules governing atomic behavior. As scientific instruments improved during the 19th and early 20th centuries, researchers began discovering that atoms were far more complex than anyone had imagined. Experiments revealed that atoms contained smaller particles, electrical charges and internal structures. Later investigations would show that atoms were not solid spheres at all, but dynamic systems shaped by the laws of quantum physics. And those laws are deeply strange. At the atomic scale, energy does not vary smoothly the way we expect. Instead, energy can exist only in certain allowed amounts, a property known as quantization. Particles sometimes behave like waves, spreading out through space in patterns of probability. Position and motion cannot both be known with perfect precision. These discoveries would eventually transform our understanding of reality. But the most remarkable part of this story is that the behavior of atoms follows precise mathematical rules. Although the atomic world can appear unpredictable, it is governed by well-defined physical principles that scientists have gradually uncovered through centuries of careful observation and experiment. These principles determine how electrons arrange themselves around atomic nuclei. They determine how atoms absorb and emit light. They determine why chemical bonds form, why materials have different properties, and why matter itself remains stable. Even something as familiar as the solidity of a table depends on atomic laws. When you place your hand on a surface, you're not actually touching solid matter in the classical sense. Instead, the electrons in your hand repel the electrons in the table through the electromagnetic force, preventing the atoms from passing through one another. The sensation of contact emerges from these invisible interactions. In other words, what we perceive as solid matter is really the result of countless atomic forces acting in delicate balance. Understanding atoms therefore means uncovering the deeper rules that govern energy, motion, and probability at the smallest scales. These rules form the foundation of modern physics and chemistry. They explain how the elements of the periodic table behave. They explain the light produced by distant stars. They even explain the complex molecules that allow life to exist. Our journey into atomic physics is not just about tiny particles. It is about discovering the hidden architecture of the universe itself. Every object around you is built from atoms following these rules. Every breath you take involves trillions of molecules moving according to the same laws discovered in laboratories and observatories across the world. And as we gradually move deeper into the story, we will begin to see how scientists uncovered those laws step by step, revealing a universe far more intricate and fascinating than anyone first imagined. As the 18th century gave way to the 19th, chemistry was beginning to transform from a craft practiced by curious experimenters into a more systematic science. Laboratories across Europe were slowly filling with balances, glassware, and carefully recorded measurements. Chemists were weighing substances before and after reactions, comparing results, and discovering that nature seemed to follow surprisingly strict numerical patterns. These patterns hinted that matter might indeed be built from discrete pieces. One of the scientists who began to recognize this was an English schoolteacher and chemist named John Dalton. Dalton lived in Manchester and spent much of his career studying gases and atmospheric phenomena. He had a careful, patient mind, and he noticed something intriguing while examining how chemical substances combined. Whenever elements reacted with one another, they did so in consistent proportions by mass. Water, for example, always formed when hydrogen and oxygen combined in the same ratio. Carbon dioxide always appeared when carbon and oxygen joined in another specific ratio. These patterns were not approximate, they were exact and repeatable. Dalton realized that such consistency would make perfect sense if matter were composed of tiny particles that combined in fixed numerical relationships. In the early 1800s, Dalton proposed a theory that gave modern science its first working atomic model. According to Dalton's atomic theory, each chemical element consists of identical atoms, and atoms of different elements have different masses. Chemical reactions, in his view, were not mysterious transformations of matter into something entirely new. Instead, reactions were rearrangements of atoms into new groupings. In other words, atoms themselves remained intact while molecules changed. Dalton's model also explained an important principle known as the law of conservation of mass. If atoms are neither created nor destroyed during chemical reactions, then the total mass of the reactants must equal the total mass of the products. Experiments consistently confirmed this idea. Dalton did not know exactly what atoms looked like, and he could not observe them directly. His picture of atoms was quite simple. He imagined them as tiny solid spheres, each type corresponding to a different element. Hydrogen atoms were small and light, oxygen atoms were heavier, and so on. Even though the model was simple, it was powerful. It allowed chemists to begin calculating how substances combined and how reactions unfolded at the microscopic level. At around the same time, scientific institutions were beginning to play a growing role in organising and advancing chemical knowledge. In London, the Royal Institution became one of the most important centres for experimental science. Established in the late 1700s, the institution supported research and public lectures aimed at exploring the laws of nature. One of the most influential figures associated with the Royal Institution was Michael Faraday. Although Faraday is more widely remembered for his work on electricity and magnetism, his experimental methods and public lectures helped shape scientific culture in Britain. His careful laboratory work demonstrated the importance of precise measurement and repeatable experiments. Across Europe, chemistry was rapidly becoming more quantitative and structured. As chemists collected data on the masses of elements and the compounds they formed, another pattern began to emerge. The properties of elements did not appear random. Certain elements behaved in strikingly similar ways. Sodium reacted violently with water. Potassium behaved almost the same way. Chlorine combined easily with both. These repeating patterns suggested that elements might be arranged into a larger organizational system. In 1869, a Russian chemist named Dmitry Mendeleev assembled one of the most famous tables in scientific history. Mendeleev arranged known chemical elements according to increasing atomic weight, while grouping together elements that shared similar chemical behavior. What he discovered was remarkable. When placed in the correct order, the properties of elements repeated at regular intervals. Elements in the same vertical column showed similar patterns of chemical reactivity, bonding behavior, and physical characteristics. This repeating structure became known as the periodic table. Mendeleev's insight went even further. In several places, the pattern suggested that certain elements should exist, even though they had not yet been discovered. Instead of ignoring these gaps, Mendeleev boldly predicted the properties of the missing elements. Later discoveries confirmed his predictions with astonishing accuracy. The periodic table quickly became one of the most powerful organizing tools in chemistry. It revealed that the elements followed a deeper order, an order that clearly reflected something fundamental about atomic structure. However, there was still a mystery. Dalton had described atoms as indivisible units, but the periodic pattern suggested that atoms must contain internal features capable of producing those repeating behaviors. Why would sodium, potassium, and lithium behave so similarly if atoms were simple solid spheres? Why would chemical properties repeat periodically across the table? The idea that atoms might contain internal components was becoming harder to ignore. Another puzzle involved atomic weight itself. When chemists measured the masses of atoms relative to hydrogen, the numbers did not always follow neat patterns. Some elements seemed slightly heavier or lighter than expected. These irregularities hinted that atomic mass might be connected to something deeper inside the atom. At this stage, scientists still had no direct evidence of what atoms were made of internally. The instruments available at the time could not probe structures smaller than molecules. But new technologies were beginning to emerge, especially those involving electricity and vacuum tubes. Researchers studying electrical currents in evacuated glass tubes began observing strange glowing rays that travelled from one electrode to another. These rays appeared to behave like streams of particles. Their properties suggested that they carried negative electrical charge. Experiments like these would eventually lead to one of the most important discoveries in atomic physics. They revealed that atoms were not indivisible after all. Instead, atoms contained smaller particles moving within them, and once scientists began exploring those particles, the simple picture of atoms as tiny billiard balls quickly dissolved. The quiet chemical atoms of Dalton's theory were about to become something far more intricate. What had once seemed like the smallest building blocks of matter would soon reveal a complex inner world of charged particles, invisible forces, and dynamic motion. The next stage of investigation would show that atoms were not merely units of chemistry. They were entire physical systems governed by deeper laws of nature. By the late 1800s, the idea that atoms were the basic building blocks of matter had become widely accepted among scientists. Chemists could explain reactions by imagining atoms combining and separating like pieces of an invisible construction set. The periodic table organized the elements into a beautifully ordered pattern, and yet, a deeper question lingered quietly in the background. Were atoms truly indivisible? For most of the 19th century, many scientists assumed they were. Dalton's original model described atoms as solid spheres, and there was little experimental evidence suggesting otherwise. But a series of curious experiments involving electricity and glass tubes began to reveal something unexpected. In laboratories across Europe, physicists were experimenting with devices known as cathode ray tubes. These tubes were made of glass and connected to electrical power supplies. When most of the air was removed from the tube, leaving a near vacuum, and a high voltage was applied across metal electrodes inside, a strange glow appeared within the tube. From the negatively charged electrode, called the cathode, a stream of invisible rays travelled across the tube toward the positively charged electrode. These mysterious rays were called cathode rays. At first, scientists debated what they actually were. Some researchers believed cathode rays were waves moving through the vacuum, somewhat like light. Others suspected they might be particles carrying electric charge. One of the scientists who studied this phenomenon most carefully was Joseph John Thomson, usually known as J.J. Thomson. Thomson worked at the Cavendish Laboratory at the University of Cambridge, one of the leading centres of experimental physics in Britain. In 1897, Thomson conducted a series of precise experiments designed to determine the nature of cathode rays. By applying electric and magnetic fields to the rays and observing how they deflected, he discovered something remarkable. The rays behaved exactly as streams of negatively charged particles would. Even more surprising was the mass of these particles. Thomson measured the ratio of electric charge to mass for the particles in the beam. The results showed that the particles were far lighter than any known atom. In fact, they were roughly 2,000 times lighter than the hydrogen atom, the lightest element known. This meant that atoms contained smaller components. Thomson had discovered the first subatomic particle, which would soon be called the electron. The discovery of the electron completely changed the picture of the atom. If electrons existed inside atoms, then atoms were not indivisible after all. Instead, they contained internal structures composed of smaller charged components. But this raised an immediate puzzle. Atoms are normally electrically neutral. They do not carry an overall electric charge, yet electrons are negatively charged. If electrons existed inside atoms, there must also be some positive charge balancing them. To explain this, Thomson proposed a new model of the atom. In this model, The atom was imagined as a sphere of positive electrical charge with negatively charged electrons embedded throughout it. The electrons were scattered inside the positively charged material, somewhat like small pieces of fruit embedded within a dessert. This model became known, somewhat humorously, as the plum pudding model. The positive charge formed the pudding, and the electrons were the plums. Although the model may sound quaint today, it represented a crucial step forward. It acknowledged that atoms had internal structure, and that electrical forces played an important role in holding that structure together. The idea also introduced a new way of thinking about matter. Atoms were no longer static objects. They were systems composed of moving charged particles interacting through electric forces. Still, many details remained uncertain. Scientists knew that electrons existed, but they did not yet know exactly how much charge each electron carried. That question was answered through a remarkable series of experiments conducted by an American physicist named Robert Millikan at the University of Chicago. Around 1909, Millikan performed what became known as the oil drop experiment. The experiment involved spraying tiny droplets of oil into a chamber between two metal plates that could be electrically charged. As the droplets fell under the influence of gravity, Millikan used an electric field to carefully adjust their motion. By balancing the gravitational force pulling the droplet downward against the electric force pushing it upward, Millikan could measure the amount of electric charge carried by each droplet. What he discovered was fascinating. The electric charges on the droplets were never random values. Instead, they always appeared as exact multiples of a single fundamental quantity. That smallest unit of electric charge corresponded to the charge carried by a single electron. Millikan's measurements showed that the electron carries an electric charge of approximately 1.6 times 10 to the minus 19 coulombs. While the number itself is extremely small, it represents one of the fundamental constants of nature. With both the charge and the mass of the electron now measured, scientists could begin understanding atoms in far greater detail. The emerging picture revealed that atoms were not solid objects at all. Instead, they were complex electrical systems containing negatively charged electrons and some form of balancing positive charge. Electrons moved within atoms and responded to electric and magnetic forces. Their behavior could influence how atoms bonded with one another, how they emitted light, and how they conducted electricity. Matter, in other words, was beginning to look more like a dynamic system of interacting charges, rather than a collection of rigid particles. This new understanding helped explain several puzzling phenomena. For example, certain materials conducted electricity easily because electrons could move through them relatively freely. In other materials, electrons were more tightly bound to atoms and could not move as easily. Electrical conductivity, magnetism, and chemical bonding all began to make more sense once electrons entered the picture. However, the plum pudding model soon encountered a serious challenge. If positive charge filled the entire atom evenly, as Thomson had suggested, then electrons should move smoothly through that positive background. But later experiments began producing results that did not quite fit that picture. Careful investigations of how particles scattered when they passed through thin materials hinted that the positive charge inside atoms might not be spread out at all. Instead, it might be concentrated in a much smaller region. This possibility would soon lead to one of the most dramatic discoveries in the history of atomic physics, revealing that nearly all of an atom's mass is packed into a tiny central core. The atom, it seemed, still had deeper secrets waiting to be uncovered. At the beginning of the 20th century, scientists were becoming increasingly confident that atoms contained internal parts. The discovery of the electron had revealed that atoms were not indivisible spheres. Instead, they were structures with moving charged particles inside them. Yet one important question remained unresolved. Where exactly was the positive charge inside the atom? According to the plum pudding model proposed by J.J. Thomson, positive charge was spread out evenly throughout the atom like a kind of invisible electrical cloud, with electrons embedded inside it. This idea seemed reasonable at first, but it had never been tested directly. That opportunity arrived through the work of a physicist originally from New Zealand named Ernest Rutherford. Rutherford had already built a strong reputation through his research on radioactivity. Working first in Montreal and later at the University of Manchester in England, he studied the energetic particles emitted by radioactive elements. These particles came in several varieties, which Rutherford classified as alpha particles, beta particles, and gamma rays. Alpha particles were particularly useful for experiments. They were relatively heavy and carried a positive electric charge. In modern terms, an alpha particle is the nucleus of a helium atom, consisting of 2 protons and 2 neutrons bound together. Because alpha particles move extremely fast and carry a positive charge, Rutherford realized they could act like tiny projectiles capable of probing the internal structure of atoms. Around 1909, Rutherford and his colleagues Hans Geiger and Ernest Marsden performed a now famous experiment that would dramatically reshape atomic theory. The setup was simple in principle, though delicate in practice. A small radioactive source emitted alpha particles in a narrow beam. This beam was directed toward a very thin sheet of gold foil, only a few hundred atoms thick. Surrounding the foil was a circular detector screen coated with a substance called zinc sulfide. Whenever an alpha particle struck the screen, it produced a tiny flash of light that could be observed through a microscope. If the plum pudding model were correct, the alpha particles should pass through the gold atoms with only slight deflections. The positive charge in the atom would be too spread out to significantly alter their paths, and in many cases that is exactly what happened. Most alpha particles travelled straight through the foil, with little or no deviation. But something surprising also occurred. A small fraction of the particles were deflected at large angles. Some even bounced almost directly backward, returning toward the source from which they had been fired. Rutherford later described his astonishment with characteristic humour. It was, he said, as if one fired a large artillery shell at a piece of tissue paper and the shell came bouncing back. This result was completely inconsistent with the plum pudding model. The only way to explain such dramatic deflections was to assume that the atom contained a region where both its mass and its positive charge were concentrated into an extremely small volume. When an alpha particle passed close to this region, the powerful electric repulsion between the positively charged alpha particle and the concentrated positive charge would deflect it sharply. Rutherford concluded that the atom must contain a tiny central core. He called this core the nucleus. The nucleus turned out to be extraordinarily small compared with the overall size of the atom. A typical atom has a diameter of roughly 1/10 of a nanometer, which is about 1/10 billionth of a meter. The nucleus, however, is roughly 100,000 times smaller than the atom itself. To visualize this difference in scale, imagine an atom enlarged until it becomes the size of a large sports stadium. In that scenario, the nucleus would be roughly the size of a small marble placed at the center of the field. Everything else inside the stadium would be empty space. This discovery revealed one of the most surprising truths about matter. Atoms are mostly empty space. The mass of the atom is concentrated almost entirely within the nucleus, while the electrons occupy the surrounding region. The nucleus itself carries positive electric charge, which balances the negative charge of the electrons. Further investigations revealed that the nucleus contains particles known as protons. Each proton carries a positive electric charge equal in magnitude to the negative charge of an electron. In a neutral atom, the number of protons in the nucleus equals the number of electrons surrounding it. However, there was still a puzzle. When scientists calculated the mass of atomic nuclei, they discovered that protons alone could not account for the total mass. Something else had to be present inside the nucleus. This mystery was solved in 1932 by the British physicist James Chadwick, who was working at the Cavendish Laboratory in Cambridge. Chadwick discovered a new type of particle inside the nucleus called the neutron. Unlike protons and electrons, neutrons carry no electric charge at all. They are electrically neutral, which is how they earned their name. Despite lacking charge, neutrons have nearly the same mass as protons. The presence of neutrons explained why atomic nuclei were heavier than expected. It also helped explain how nuclei could remain stable. Inside the nucleus, positively charged protons repel each other through the electromagnetic force. Because like charges repel, a cluster of protons should naturally push itself apart. Yet atomic nuclei do not simply explode. Something must be holding them together. The force responsible for this stability is known as the strong nuclear force. It is one of the fundamental forces of nature, alongside gravity, electromagnetism, and the weak nuclear force. The strong nuclear force acts between protons and neutrons at extremely short distances. When particles are close enough together inside the nucleus, this force becomes incredibly powerful, strong enough to overcome the electromagnetic repulsion between protons. As a result, protons and neutrons bind together to form stable nuclei. The strong nuclear force operates over distances of only a few femtometers, which is about 1/4 of a meter. Outside that tiny range, its strength rapidly fades, but within the nucleus, it dominates all other forces. The balance between the repulsive electromagnetic force and the attractive strong nuclear force determines which nuclei are stable and which are unstable. In heavier elements, this balance becomes delicate, and some nuclei eventually undergo radioactive decay as they seek more stable configurations. With the discovery of the nucleus, protons, and neutrons, the atom was no longer a simple object. It had become a miniature planetary system of sorts, with a dense central core surrounded by electrons. But unlike the solar system, where planets orbit through empty space following classical laws of motion, the behavior of electrons inside atoms would soon reveal something even stranger. The deeper scientists looked into the atom, the more it became clear that entirely new physical rules were required to describe what was happening there. And those rules would soon lead to one of the most profound revolutions in the history of science. By the early years of the 20th century, the structure of the atom seemed to be coming into focus. Experiments had revealed a tiny, dense nucleus carrying positive charge. Electrons, light and negatively charged, occupied the space around that nucleus. At first glance, the arrangement almost resembled a miniature solar system, with electrons moving around the central core much like planets orbit the sun. It was an appealing picture, familiar, even comforting. Yet there was a serious problem hiding inside it. According to the well-established laws of classical physics, such an atom should not be able to exist at all. To understand why, it helps to recall what classical electrodynamics says about charged particles. Electrons carry electric charge. Whenever an electrically charged particle accelerates, classical theory predicts that it must emit electromagnetic radiation. This radiation carries energy away from the particle. And here lies the difficulty. If an electron were orbiting the nucleus in a circular path, it would constantly be accelerating. Even though its speed might remain constant, its direction would be changing continuously as it curved around the nucleus. In physics, any change in velocity, whether in speed or direction, counts as acceleration. Therefore, according to classical electrodynamics, an orbiting electron must continuously radiate energy. But if the electron radiates energy, it loses energy. As it loses energy, its orbit would shrink. The electron would spiral inward toward the nucleus, moving faster and faster as it approached. Calculations performed at the time suggested that such a collapse would happen incredibly quickly. An electron orbiting a nucleus should lose enough energy to crash into it in roughly 1/10 billionth of a second. In other words, classical physics predicted that atoms should be catastrophically unstable, and yet, clearly they are not. The atoms that make up your body have existed for billions of years. The atoms inside a piece of rock can remain stable for geological ages. Matter does not collapse into itself in a tiny fraction of a second. The stability of atoms presented a profound contradiction. If classical physics were correct, atoms should not exist. Yet atoms obviously do exist. Something in the prevailing theory had to be missing. This realization produced what historians of science often describe as a crisis in physics. By the turn of the 20th century, many scientists believed that the fundamental laws of nature were already understood. Newton's laws described motion. James Clerk Maxwell's equations explained electricity, magnetism, and light. Thermodynamics accounted for heat and energy. But experiments involving atoms and radiation were beginning to reveal cracks in this seemingly complete framework. One of the first clues came from an unexpected source: the study of heat and light emitted by hot objects. When any object is heated, it begins to glow. A piece of iron placed in a furnace gradually shifts from dull red to bright orange, and eventually to white as its temperature increases. The glowing light emitted by hot objects is known as thermal radiation. Physicists in the late 19th century attempted to calculate how much radiation a hot object should emit at different wavelengths. To simplify the problem, they imagined a perfect radiator known as a blackbody. A blackbody absorbs all incoming radiation and emits energy in a characteristic spectrum determined only by its temperature. Theoretical calculations based on classical physics predicted something strange. As the wavelength of radiation became shorter and shorter, corresponding to higher frequencies of light, the amount of emitted energy should increase without limit. According to the equations, a hot object should release an enormous amount of energy at extremely short wavelengths, including ultraviolet and beyond. This prediction became known as the ultraviolet catastrophe. Fortunately for everyone nearby, real objects do not behave this way. Measurements showed that the energy emitted by a black body rises to a peak at a certain wavelength and then falls off again at shorter wavelengths. The classical theory failed dramatically to match the observed data. In 1900, a German physicist named Max Planck found a way to solve the puzzle. Planck was studying black-body radiation at the University of Berlin, and after considerable mathematical effort he discovered a formula that matched experimental measurements perfectly. However, the formula required an unusual assumption. Planck proposed that energy could not be emitted or absorbed in arbitrary amounts. Instead, energy was exchanged in discrete packets, which he called quanta. The amount of energy carried by each packet was proportional to the frequency of the radiation. Planck's relation can be expressed in words as energy equals Planck's constant multiplied by frequency. The constant in this equation, now called Planck's constant, has a value of approximately 6.63 times 10 to the minus 34 joule-seconds. It is an extraordinarily small number, which is why quantization is not noticeable in everyday life. At atomic scales, however, this discrete structure of energy becomes essential. Planck himself initially regarded the idea of quantized energy as a mathematical trick rather than a deep physical principle, but the concept would soon take on much greater significance. A few years later, in 1905, Albert Einstein applied Planck's idea to another puzzling phenomenon known as the photoelectric effect. The photoelectric effect occurs when light shines on certain metals and causes them to emit electrons. Experiments showed that electrons were ejected only when the light exceeded a specific frequency. Increasing the brightness of lower frequency light did not produce the effect, no matter how intense the light became. Classical wave theory could not explain this behavior. If light were simply a continuous wave carrying energy smoothly across space, increasing the intensity should eventually provide enough energy to free electrons from the metal surface. But experiments showed that frequency mattered far more than intensity. Einstein proposed a bold explanation. He suggested that light itself is composed of individual packets of energy, later called photons. Each photon carries energy proportional to its frequency, again following the relation energy equals Planck's constant multiplied by frequency. When a photon strikes an electron in a metal, it transfers its energy in a single interaction. If the photon's energy is high enough, the electron can escape from the surface. Einstein's explanation matched the experimental results perfectly. It also suggested something remarkable. Light, which had long been understood as a wave, also behaves like a particle. These discoveries began to reveal that nature does not always follow the intuitive rules described by classical physics. Energy could come in discrete units. Light could behave as both wave and particle, and the structure of atoms could not be explained using the existing theories of motion and electromagnetism alone. A new framework was required. The stability of atoms, the behavior of radiation, and the emerging evidence from experiments all pointed toward a deeper set of laws governing the microscopic world. Those laws would soon form the foundation of an entirely new branch of physics, quantum theory. At the beginning of the 20th century, the atom had become a fascinating puzzle. Scientists knew that atoms contained a dense nucleus surrounded by electrons, but the behavior of those electrons remained deeply mysterious. Classical physics predicted that electrons orbiting a nucleus should continuously radiate energy and spiral inward, leading to the rapid collapse of the atom. Yet atoms clearly remained stable. The challenge was to understand how electrons could exist around the nucleus without losing energy and falling inward. One of the scientists who took on this challenge was a young Danish physicist named Niels Bohr. Bohr had studied under Ernest Rutherford in Manchester, where the nuclear model of the atom had been established. Rutherford's picture placed nearly all of an atom's mass and positive charge in a tiny nucleus, with electrons surrounding it. But Rutherford himself had not solved the stability problem. Bohr believed that the answer might lie in the new ideas about quantized energy that had recently emerged from the work of Max Planck and Albert Einstein. In 1913, Bohr proposed a new model of the hydrogen atom that combined Rutherford's nuclear structure with Planck's concept of quantization. Hydrogen was an ideal starting point because it is the simplest atom in the universe. It contains a single proton in its nucleus and one electron orbiting around it. Bohr suggested that electrons could not orbit the nucleus at arbitrary distances. Instead, only certain specific orbits were allowed. These orbits corresponded to fixed energy levels. An electron in one of these permitted orbits would not radiate energy, even though it was accelerating. This was a radical departure from classical electrodynamics. Bohr simply postulated that these stable orbits existed and that electrons could occupy them without losing energy. Energy was emitted or absorbed only when an electron jumped from one orbit to another. When an electron dropped from a higher energy orbit to a lower one, the atom released energy in the form of light. Conversely, if an electron absorbed energy, it could move to a higher orbit. The energy of the emitted light depended on the difference between the two energy levels involved in the transition. Bohr's model captured this relationship using a simple principle that followed from Planck's earlier work. The energy carried by the emitted light could be expressed as energy equals Planck's constant multiplied by frequency. This meant that the color of the light produced by the atom corresponded directly to the energy difference between the electron's initial and final states. Remarkably, Bohr's model successfully explained a long-standing mystery in spectroscopy. When scientists passed electricity through hydrogen gas, the atoms emitted light at specific, sharply defined wavelengths, rather than producing a continuous rainbow of colors. These distinct colors formed what is known as the hydrogen emission spectrum. The pattern of spectral lines had been measured with great precision by spectroscopists such as Johann Balmer and Johannes Rydberg during the 19th century, but no one had understood why those particular wavelengths appeared. Bohr's quantized orbits provided the answer. Each spectral line corresponded to an electron jumping between specific energy levels in the hydrogen atom. The mathematics of Bohr's model predicted the wavelengths of these lines with impressive accuracy. For the first time, the structure of the atom was directly connected to measurable patterns of light. Spectroscopy soon became one of the most powerful tools for studying atomic structure. By examining the wavelengths of light emitted or absorbed by atoms, scientists could infer details about the energy levels of electrons and the internal structure of different elements. Astronomers even used these spectral fingerprints to identify elements in distant stars. The same atomic transitions that occurred in laboratory gases also occurred in the atmospheres of stars across the universe. Despite its success, Bohr's model was not the final answer. Soon after its introduction, scientists realized that the model worked extremely well for hydrogen, but struggled when applied to more complicated atoms. Atoms containing multiple electrons exhibited spectra that were far more complex than Bohr's simple energy levels could explain. Physicists also noticed subtle details in hydrogen's spectral lines that the original model did not fully capture. One of the scientists who attempted to refine Bohr's model was the German physicist Arnold Sommerfeld. Working in Munich during the early 1900s, Sommerfeld expanded the theory by allowing electron orbits to take on elliptical shapes rather than perfectly circular paths. He also incorporated ideas from Einstein's theory of special relativity, recognizing that electrons moving close to the speed of light would experience relativistic effects that slightly altered their energy levels. Sommerfeld's modifications introduced additional quantum numbers that helped explain fine details in atomic spectra, including what became known as fine structure splitting. These tiny shifts in spectral lines arise from subtle changes in electron energy levels due to relativistic motion and other effects. While Sommerfeld's improvements made the model more accurate, the theory still relied on somewhat artificial assumptions about electron orbits. Electrons were treated as particles moving along precise paths around the nucleus, similar to planets orbiting the Sun. But the growing evidence from experiments suggested that the microscopic world did not behave quite like a miniature solar system. Around the same time, physicists were beginning to encounter phenomena that hinted at a deeper dual nature of matter itself. If light could behave both as a wave and as a particle, as Einstein had suggested, perhaps particles such as electrons might also display wave-like properties. This possibility would soon open the door to a radically new description of the atom. Instead of electrons following fixed paths around the nucleus, scientists would begin to describe them as waves spread through space, forming patterns of probability rather than precise orbits. The familiar planetary picture of the atom would gradually give way to something far stranger, yet far more accurate. By the early 1920s, physics had reached an unusual point in its development. Light, which had long been understood as a wave spreading through space, was now known to behave like a stream of particles when interacting with matter. Albert Einstein's explanation of the photoelectric effect had demonstrated that light sometimes arrives in discrete packets of energy called photons. This realization raised an intriguing question. If waves of light could sometimes behave like particles, might the reverse also be true? Could particles behave like waves? This bold idea was proposed in 1924 by a young French physicist named Louis de Broglie. De Broglie came from an aristocratic family in France, but his curiosity led him toward theoretical physics. While studying the strange dual nature of light, he began wondering whether the same principle might apply to matter itself. De Broglie suggested that every particle, including electrons, should possess a wave-like character. According to his proposal, a particle moving through space is associated with a wavelength determined by its momentum. Momentum is a measure of motion and is equal to mass multiplied by velocity. De Broglie expressed the relationship between momentum and wavelength in a remarkably simple form. Wavelength equals Planck's constant divided by momentum. Planck's constant, the tiny number first introduced by Max Planck in his work on blackbody radiation, once again appeared as a fundamental quantity governing the microscopic world. Although the equation may look simple when written in mathematical form, its meaning is profound. It suggests that matter is not purely particle-like. Instead, every moving particle carries an associated wave. For everyday objects, this wave nature is far too small to observe. Consider a baseball travelling through the air. Because the baseball has a relatively large mass, its momentum is enormous compared with that of an electron. When Planck's constant is divided by that large momentum, the resulting wavelength becomes unimaginably tiny. The wave associated with a baseball would have a wavelength far smaller than the diameter of an atomic nucleus. Detecting such a wave would be essentially impossible. Electrons, however, are vastly lighter. An electron has a mass roughly 2,000 times smaller than that of a hydrogen atom. When electrons move at moderate speeds inside atoms or laboratory experiments, their associated wavelengths fall into a range comparable to the spacing between atoms in a crystal. And when a wavelength becomes comparable to the size of structures it encounters, wave behavior can appear in dramatic ways. One of the most characteristic features of waves is diffraction. Diffraction occurs when waves encounter obstacles or narrow openings and spread out, producing patterns of interference. Water waves passing through a narrow gap create rippling patterns. Light passing through slits produces bright and dark bands on a screen. If electrons truly behaved like waves, they should produce similar patterns. The first convincing experimental confirmation came in 1927 at Bell Telephone Laboratories in the United States. Two physicists, Clinton Davison and Lester Germer, were studying how electrons scattered when fired at a crystal surface. Their experiment involved directing a beam of electrons toward a carefully prepared nickel crystal and measuring how the electrons scattered at different angles. Initially, their goal was simply to understand electron interactions with solid materials. But something unexpected happened. Instead of scattering randomly, the electrons formed a pattern of peaks and valleys in intensity, very similar to the diffraction patterns produced by waves passing through a regular structure. The crystal lattice of the nickel acted like a diffraction grating, and the electrons behaved exactly as de Broglie's theory predicted. Davison and Germer had inadvertently demonstrated that electrons produce diffraction patterns, just like waves of light. Around the same time, an independent experiment in England reached the same conclusion. The physicist George Paget Thomson, working at the University of Aberdeen and later at Imperial College London, passed beams of electrons through extremely thin metal foils. When the electrons emerge from the foil, they produce circular diffraction patterns on photographic plates. These patterns resembled the interference rings created by waves passing through narrow openings. George Paget Thomson's work carried an additional historical twist. His father, J.J. Thomson, had discovered the electron as a particle only a few decades earlier. Now the son had demonstrated that the same particle behaved like a wave. Physics had arrived at an extraordinary realization. Electrons were neither simple particles nor simple waves. They possessed aspects of both. This dual nature of matter and radiation became one of the central principles of quantum physics. Depending on how an experiment is arranged, electrons can display properties that resemble particles in some situations and waves in others. Inside atoms, this wave behavior plays a crucial role. Instead of imagining electrons as tiny objects orbiting the nucleus along precise circular paths, physicists began thinking of them as waves distributed through space. These waves do not spread out endlessly. They form stable patterns around the nucleus, much like standing waves on a vibrating string. A standing wave occurs when waves reflect back and forth within a confined region, producing fixed patterns of peaks and nodes. Musical instruments provide a familiar example. When a guitar string vibrates, only certain wavelengths can form stable standing waves along its length. The allowed vibrations depend on the length of the string and the boundary conditions at its ends. In a similar way, electrons inside atoms can only form standing waves that fit around the nucleus in particular patterns. Each allowed pattern corresponds to a specific energy level. This perspective offered a deeper explanation for the quantized energy levels first introduced by Niels Bohr. Instead of being arbitrary rules imposed on electron orbits, the allowed energy levels arose naturally from the wave nature of electrons. Only certain wave patterns could exist stably around the nucleus. While this idea provided an elegant conceptual picture, describing these electron waves precisely required a powerful mathematical framework. Scientists needed a way to calculate the shapes of these waves, their energies, and how they evolved over time. Developing that framework would soon become one of the greatest achievements in the history of physics. As the idea that particles could behave like waves began to gain acceptance, physicists faced a new challenge. If electrons truly possessed wave-like properties, then scientists needed a mathematical framework capable of describing those waves in detail. The question was no longer simply whether matter behaved like waves, but how those waves evolved through space and time. The answer arrived through the work of an Austrian physicist named Erwin Schrödinger. In 1926, while working in Zurich, Schrödinger developed a mathematical equation that would become one of the central foundations of modern physics. This equation provided a way to calculate how quantum systems change over time. It described the behavior of the wave associated with a particle, including electrons moving inside atoms. Today it is known as the Schrödinger equation. Although the full mathematical form of the equation can appear intimidating, its core idea is surprisingly elegant. Schrödinger's equation relates the energy of a system to the spatial behavior of a wave associated with a particle. By solving the equation under specific conditions, scientists can determine the allowed wave patterns for electrons bound to atomic nuclei. In simplified terms, the equation expresses how the total energy of a quantum system is connected to the shape and curvature of its wave pattern. When written conceptually in words, the relationship can be expressed as the total energy of the quantum system equals the kinetic energy contribution plus the potential energy contribution. This simple statement hides a great deal of mathematical depth, but its physical meaning is clear. The behavior of a quantum particle depends both on its motion and on the forces acting upon it. The wave described by the Schrödinger equation is called the wave function. The wave function contains all the information that can be known about a quantum system. It varies through space and time, forming patterns that reflect the underlying physics of the system being studied. At first, physicists struggled to understand what the wave function actually represented. Was it a physical wave similar to a ripple on water? Was it a real oscillation of some unknown substance filling space? The answer came through the insight of the German physicist Max Born. Born proposed that the wave function should not be interpreted as a physical wave in the traditional sense. Instead, the wave function represents a probability distribution. The value of the wave function at any point in space describes the likelihood of finding the particle at that location. More precisely, the square of the wave function gives the probability density. In practical terms, this means that electrons inside atoms do not follow precise trajectories like tiny planets. Instead, they exist as clouds of probability surrounding the nucleus. Certain regions of space have higher probability for finding the electron, while other regions are less likely. This probabilistic interpretation represented a major conceptual shift in physics. For centuries, scientists had assumed that the motion of objects could be described exactly if enough information were known. Newton's laws, for example, allow precise predictions of planetary orbits given the correct starting conditions. Quantum mechanics introduced a different kind of description. Instead of predicting exact positions and paths, it provides probabilities. The theory can tell us where an electron is most likely to be found, but not exactly where it will appear in any individual measurement. When the Schrödinger equation is solved for the hydrogen atom, it produces a series of stable wave patterns surrounding the nucleus. Each pattern corresponds to a specific energy level, similar to the discrete levels first proposed in Bohr's model, However, the new wave description reveals far richer structures. These wave patterns form three-dimensional shapes called atomic orbitals. An orbital does not represent a path or orbit in the classical sense. Instead, it describes the spatial region where an electron is most likely to be found. Different orbitals have different shapes. Some are spherical, forming a cloud surrounding the nucleus. Others resemble dumbbells extending in opposite directions. Still others form complex clover-shaped structures that stretch through space in intricate patterns. These shapes arise directly from the mathematics of the Schrödinger equation. When physicists solve the equation for an electron bound to a nucleus, they find that only certain wave patterns satisfy the conditions required for stability. Each allowed solution corresponds to a particular set of quantum numbers that describe the energy, angular momentum, and orientation of the electron's wave pattern. The allowed energy levels predicted by the equation match the spectral lines observed in hydrogen with extraordinary precision. The colors of light emitted by hydrogen atoms correspond exactly to transitions between the quantized energy levels predicted by the theory. Spectroscopy, the study of light emitted and absorbed by atoms, became one of the most powerful tools for confirming quantum theory. The patterns of spectral lines measured in laboratories match the mathematical predictions of the Schrödinger equation to remarkable accuracy. The success of these calculations demonstrated that the strange probabilistic description of electrons was not merely a philosophical curiosity, it was a precise and reliable representation of physical reality at the atomic scale. As the theory developed further, physicists sought to place its mathematical foundations on an even firmer footing. One of the scientists who played a crucial role in this effort was the Hungarian mathematician John von Neumann. Working in the late 1920s and early 1930s, von Neumann reformulated quantum mechanics using advanced mathematical structures known as Hilbert spaces. His work provided a rigorous framework for describing quantum states, operators, and measurements. In von Neumann's formulation, the wave function becomes a vector in an abstract mathematical space, and physical quantities such as energy or momentum are represented by operators acting on that space. Although this description may sound abstract, it allows physicists to analyze quantum systems with extraordinary precision. The formalism developed by von Neumann still underpins much of modern quantum theory. Through this mathematical framework, the strange behavior of atoms becomes predictable and consistent. The shapes of atomic orbitals determine how atoms bond with one another to form molecules' message delivery timed out. Please try again. Retry. The idea that electrons behave like waves raised an important challenge. If electrons truly possessed wave-like properties, then scientists needed a precise way to describe those waves. The simple planetary picture of electrons orbiting a nucleus was no longer sufficient. Instead, the atom had become a system in which invisible waves shaped the behavior of matter itself. To move forward, physicists required a mathematical language capable of describing how these waves behaved. One of the scientists who provided that language was the Austrian physicist Erwin Schrödinger. In 1926, Schrödinger introduced a powerful equation that became one of the central pillars of quantum physics. His work built directly upon the earlier ideas of Louis de Broglie, who had proposed that particles possess wave-like properties. Schrödinger asked a natural question. If electrons behave like waves, what equation describes how those waves move and evolve? The result of his investigation was the Schrödinger equation. In its most general form, the Schrödinger equation describes how a quantum system changes with time. It connects the total energy of a system with the mathematical object that represents its wave behavior, known as the wave function. When expressed in words, the basic idea can be summarized as the total energy of a quantum system equals the kinetic energy plus the potential energy acting on the wave function. Although the equation itself is typically written using mathematical symbols, its meaning is straightforward in principle. It provides a rule that determines how the wave associated with a particle behaves under the influence of forces. Solving the Schrödinger equation for a particular system reveals the possible states that the system can occupy. Each solution corresponds to a specific energy level and a specific pattern in the wave function. But what exactly is a wave function? At first, Schrödinger himself imagined the wave function as a kind of physical wave spread through space. However, this interpretation soon proved difficult to maintain. The wave function does not represent a tangible oscillation like a water wave or a sound wave. Instead, its meaning was clarified by the German physicist Max Born. In 1926, Born proposed what became known as the probabilistic interpretation of the wave function. According to Born's interpretation, the wave function does not describe a physical wave of matter. Rather, it describes the probability of finding a particle in a particular region of space. If the wave function has a large magnitude in a certain location, the particle is more likely to be detected there. If the wave function is small in another region, the particle is less likely to appear there. In other words, the wave function encodes information about probability. This interpretation marked a profound shift in the philosophy of physics. Classical physics aimed to describe precise trajectories of objects. If one knew the position and velocity of a planet, Newton's laws allowed its future path to be calculated exactly. Quantum physics operates differently. Instead of predicting exact paths, it predicts probabilities. The theory can determine where an electron is likely to be found, but it does not assign the electron a single definite path through space. The Schrödinger equation, therefore, does not produce orbits in the classical sense. Instead, it produces patterns of probability. When the Schrödinger equation is solved for an electron bound to a nucleus, the solutions correspond to specific energy levels and spatial patterns of probability. These patterns are known as atomic orbitals. An orbital is not a physical path. It is a region of space where the probability of finding the electron is relatively high. Different orbitals have distinct shapes. Some resemble spheres surrounding the nucleus. Others form lobed structures extending in particular directions. These shapes arise naturally from the mathematical solutions of the Schrödinger equation. The simplest orbital, associated with the lowest energy state of the hydrogen atom, forms a roughly spherical cloud around the nucleus. More energetic orbitals exhibit increasingly complex geometries. These patterns may sound abstract, but they have measurable consequences. The arrangement of electrons in orbitals determines the chemical properties of elements. The way atoms bond together to form molecules depends on the shapes and energies of these orbitals. Even the structure of the periodic table reflects the way electrons occupy different orbital patterns around atomic nuclei. The mathematics behind these ideas soon grew more sophisticated. As quantum theory developed, physicists began seeking a deeper and more rigorous framework for understanding the wave function and the rules governing quantum systems. One of the most important figures in this effort was the Hungarian mathematician and physicist John von Neumann. Working during the late 1920s and early 1930s, von Neumann helped place quantum mechanics on a solid mathematical foundation. His work introduced advanced mathematical structures known as Hilbert spaces, which provided a formal setting in which wave functions could be studied. Within this framework, quantum states are represented as vectors in an abstract mathematical space. Physical quantities such as energy, position, and momentum are represented by mathematical operators that act on those vectors. Although the formalism can appear highly abstract, it allowed physicists to develop quantum mechanics with remarkable precision and consistency. Von Neumann's work also addressed one of the most subtle aspects of quantum theory: measurement. When a measurement is made on a quantum system, the wave function appears to change suddenly, collapsing into a definite outcome. Understanding how and why this collapse occurs remains one of the most fascinating questions in the foundations of physics. Despite these conceptual challenges, the mathematical framework of quantum mechanics has proven extraordinarily successful. The Schrödinger equation accurately predicts the energy levels of atoms. Spectral lines measured in laboratories match the calculated transitions between quantum states. Chemical bonding, electrical conductivity, and countless other phenomena can be explained using the same mathematical principles. Modern technologies rely heavily on this understanding. Lasers, semiconductors, magnetic resonance imaging, and atomic clocks all operate according to quantum laws first described by the Schrödinger equation and its mathematical extensions. What began as an attempt to understand the strange wave nature of electrons eventually became a comprehensive theory describing the behavior of matter at its most fundamental level. Yet even with this powerful mathematical machinery, the quantum world continued to challenge intuition. The deeper scientists explored, the clearer it became that certain limits existed on what could be known about particles such as electrons. Those limits were not due to imperfections in measurement instruments. They were built directly into the structure of nature itself. As physicists explored the newly emerging framework of quantum mechanics during the 1920s, one idea began to stand out as both profound and unsettling. The theory suggested that there are fundamental limits to what can be known about the properties of particles. This concept was articulated most clearly by the German physicist Werner Heisenberg. Heisenberg was one of the central figures in the development of quantum theory. Working alongside Max Born and Pascual Jordan in the mid-1920s, he helped create an alternative mathematical formulation of quantum mechanics known as matrix mechanics. Unlike Schrödinger's wave approach, matrix mechanics described quantum systems using arrays of numbers representing observable quantities such as energy and momentum. Although the mathematical details were quite different, both approaches ultimately produced the same predictions. While exploring these ideas, Heisenberg discovered a remarkable principle that would reshape the understanding of measurement and knowledge in physics. This principle became known as the uncertainty principle. In simple terms, the uncertainty principle states that certain pairs of physical quantities cannot both be known with unlimited precision at the same time. The most famous example involves position and momentum. Position describes where a particle is located. Momentum describes how fast it is moving and in which direction. Heisenberg showed that the uncertainties in position and momentum obey a fundamental relationship. The uncertainty in position multiplied by the uncertainty in momentum is greater than or equal to Planck's constant divided by 4 pi. Although the mathematical expression may appear technical, its meaning is surprisingly clear. The more precisely one determines the position of a particle, the less precisely its momentum can be known. Conversely, if the momentum is measured with high precision, the particle's position becomes less certain. This limitation does not arise from experimental imperfections. It is not caused by poor instruments or insufficient technology. Even a perfectly designed experiment cannot avoid the uncertainty principle. The limitation exists because particles such as electrons exhibit wave-like properties. To see why this happens, imagine trying to pinpoint the location of a wave. A perfectly localized wave would require combining many different wavelengths together. But when a wave contains many wavelengths, its momentum becomes uncertain. Conversely, a wave with a single precise wavelength has a well-defined momentum but spreads out across space, making its position uncertain. Electrons, behaving as quantum waves, must obey this same principle. The uncertainty principle therefore reflects the deep structure of quantum systems. It is not merely a statement about measurement. It is a statement about how nature itself operates at microscopic scales. One of the immediate consequences of this principle is that electrons inside atoms cannot have precise trajectories. The idea of an electron following a definite orbit around the nucleus, like a planet circling a star, becomes impossible. Instead, the electron's location must be described using probability. This is where the concept of the electron cloud emerges. Rather than imagining a tiny particle tracing a path through space, physicists describe the electron as occupying a cloud of probability surrounding the nucleus. Within this cloud, certain regions have higher probability densities, meaning the electron is more likely to be found there if a measurement is performed. These probability distributions correspond to the orbitals calculated from the Schrödinger equation. The shapes of these orbitals reflect the standing wave patterns formed by the electron's wave function. The uncertainty principle also plays a crucial role in the stability of atoms. If an electron could be localized precisely at the nucleus, it would effectively collapse into that position. But doing so would require the electron's momentum to become extremely uncertain. That large uncertainty in momentum corresponds to extremely high kinetic energy. In effect, the uncertainty principle prevents electrons from being confined too tightly around the nucleus. This balance between localization and kinetic energy helps stabilize atomic structure. Even though the principle places limits on knowledge, it does not render physics powerless. Quantum theory still allows extremely accurate predictions about measurable outcomes. Physicists can calculate the probability that an electron will be found in a particular region, the energy levels of atoms, and the frequencies of light emitted during atomic transitions. Experiments repeatedly confirm these predictions with extraordinary precision. What quantum mechanics changes is not the ability to make predictions, but the nature of those predictions. Instead of describing exact trajectories, the theory describes distributions of possible outcomes. This shift from certainty to probability represents one of the most profound conceptual changes in the history of science. Yet despite its philosophical implications, the uncertainty principle has proven remarkably practical. Modern technologies, including scanning tunneling microscopes and semiconductor devices, rely directly on quantum effects governed by this principle. The quantum world may limit what can be known simultaneously, but it also reveals a deeper structure underlying matter itself. As quantum theory matured during the 1920s, physicists began noticing that particles did not all behave in exactly the same statistical ways. When large numbers of particles are present, the rules governing how they arrange themselves become incredibly important. These statistical rules determine how energy spreads through systems, how particles occupy available states, and ultimately how matter itself is structured. The first major step in understanding these patterns came from a physicist working far from the traditional centres of European science. In 1924, an Indian physicist named Satyendra Nath Bose was studying the behaviour of light. Bose was teaching at the University of Dhaka in what is now Bangladesh. While analysing the statistical distribution of photons, the particles of light, he developed a new method for counting the possible ways energy could be distributed among them. What made Bose's approach unusual was that he treated photons as completely indistinguishable from one another. In classical physics, particles are considered distinct individuals. If two classical particles exchange positions, that counts as a different configuration. But Bose realised that for photons, swapping two identical particles does not produce a physically different state. The particles cannot be labelled or tracked individually. In a deep sense, they are truly identical. Using this insight, Bose derived a new statistical distribution describing how photons occupy different energy states. He sent his paper to Albert Einstein, who immediately recognised its significance. Einstein translated the paper into German and arranged for it to be published. He then extended Bose's method beyond photons to other types of particles. Together, their work produced what is now known as Bose-Einstein statistics. Particles that follow Bose-Einstein statistics are called bosons, a name chosen to honour Satyendra Nath Bose. Bosons include photons, as well as other particles such as gluons and certain atomic nuclei. Bosons share a remarkable property. Multiple bosons can occupy exactly the same quantum state simultaneously. In other words, they can pile into the same energy level without restriction. This behaviour leads to fascinating physical phenomena. Under extremely cold conditions, large numbers of bosons can condense into a single quantum state, forming a collective wave that behaves almost like a single giant particle. This state of matter, known as a Bose-Einstein condensate, was first created experimentally in 1995 by Eric Cornell and Carl Wieman at the University of Colorado. While Bose and Einstein were uncovering the statistical rules governing bosons, another group of physicists was investigating particles that behaved quite differently. In 1926, the Italian physicist Enrico Fermi developed a statistical description for particles that obey a different set of rules. At nearly the same time, the British physicist Paul Dirac independently arrived at the same theory. Their work became known as Fermi-Dirac statistics. Particles that follow Fermi-Dirac statistics are called fermions, in honour of Enrico Fermi. Electrons belong to this category, as do protons and neutrons. Unlike bosons, fermions obey a strict rule. No two identical fermions can occupy the same quantum state at the same time. This restriction arises from a deeper principle discovered by the Austrian physicist Wolfgang Pauli. In 1925, Pauli introduced what is now called the Pauli exclusion principle. The principle states that no two electrons in an atom can possess exactly the same set of quantum numbers. Quantum numbers are the mathematical labels that describe the allowed states of electrons within atoms. Each electron in an atom is characterized by 4 quantum numbers. These numbers describe the electron's energy level, its orbital shape, its orientation in space, and its intrinsic property known as spin. The Pauli exclusion principle ensures that every electron must occupy a unique quantum state. At first glance, this rule may seem like an obscure technical detail. In reality, it has enormous consequences for the structure of matter, because electrons cannot share identical quantum states. They must fill available energy levels one by one. Low energy levels fill first, followed by higher ones as more electrons are added. This process creates the layered structure of electron shells surrounding atomic nuclei. In the hydrogen atom, which contains only one electron, the situation is simple. That electron occupies the lowest available energy state. But in atoms with many electrons, the exclusion principle forces electrons to distribute themselves across multiple orbitals and shells. The arrangement of electrons within these shells determines the chemical properties of elements. For example, The outermost electrons in an atom, often called valence electrons, are primarily responsible for chemical bonding. Elements with similar numbers of valence electrons tend to behave in similar ways chemically. This pattern is precisely what appears in the periodic table. Elements are arranged according to increasing atomic number, which corresponds to the number of protons in the nucleus, and, in neutral atoms, the number of electrons surrounding it. As electrons fill successive shells and orbitals according to quantum rules, the chemical properties of elements repeat periodically. The periodic table, first organized by Dmitry Mendeleev in the 19th century, turns out to reflect the underlying quantum structure of atoms. For example, the noble gases such as helium, neon, and argon possess completely filled outer electron shells. This configuration makes them chemically stable and relatively unreactive. Alkali metals such as sodium and potassium each have a single electron in their outermost shell. This lone electron is relatively easy to remove, making these elements highly reactive. All of these patterns arise from the interplay between quantum mechanics, Fermi-Dirac statistics, and the Pauli exclusion principle. Quantum statistics therefore shapes the architecture of matter itself. The structure of atoms, the behavior of chemical elements, the properties of metals and insulators, and even the stability of dense astrophysical objects such as white dwarf stars, all depend on the statistical rules governing fermions and bosons. Inside a white dwarf star, for example, enormous gravitational forces attempt to compress matter into a smaller and smaller volume. But the Pauli exclusion principle prevents electrons from occupying the same quantum states, creating a pressure known as electron degeneracy pressure. This quantum mechanical effect can resist gravity and stabilize the star. From the behavior of light to the structure of atoms and the fate of collapsing stars, quantum statistics plays a central role. What began as an abstract investigation into the counting of quantum states ultimately revealed the deep rules governing how matter organizes itself throughout the universe. As quantum mechanics developed during the 1920s and 1930s, physicists gradually realized that something deeper than individual equations was shaping the behavior of atoms. Beneath the complicated mathematics of wave functions and probability distributions lay a surprisingly elegant organizing principle. That principle was symmetry. In everyday language, symmetry usually means balance or visual harmony. A snowflake looks symmetrical because its patterns repeat in multiple directions. A circle looks the same when rotated around its center. In physics, symmetry has a more precise meaning. A system is said to possess symmetry if certain transformations leave its fundamental properties unchanged. Rotating an object, shifting it in space, or reversing time might alter its appearance, but the underlying physical laws remain the same. For many years, scientists suspected that symmetry must play an important role in the laws of nature, but the exact connection remained unclear until a remarkable mathematical insight emerged from the work of a German mathematician named Emmy Noether. In 1918, while working at the University of Göttingen, Noether proved a theorem that would become one of the most profound results in theoretical physics. Noether's theorem states that every continuous symmetry in the laws of physics corresponds to a conservation law. This idea links abstract mathematical symmetry with measurable physical quantities. For example, if the laws of physics remain the same when time moves forward, then energy must be conserved. If the laws remain unchanged when a system is shifted in space, then momentum is conserved. Perhaps most relevant for atoms, if the laws of physics remain unchanged when a system is rotated, then angular momentum is conserved. Angular momentum describes rotational motion. It is the quantity that determines how spinning objects behave, whether they are spinning planets, rotating wheels, or electrons moving within atoms. Inside atoms, electrons possess angular momentum, even though they are not literally spinning like tiny solid balls. Instead, their wave functions carry angular momentum as a fundamental property of their quantum state. This property plays a crucial role in determining the allowed configurations of electrons around the nucleus. When physicists solve the Schrödinger equation for electrons in atoms, the solutions naturally include angular momentum quantum numbers. These quantum numbers describe how the electron's wave function behaves under rotations in space. Some wave functions remain unchanged when rotated, corresponding to zero angular momentum. Others transform in more complex ways, producing shapes with lobes, rings, and directional patterns. These mathematical structures determine the familiar shapes of atomic orbitals. The spherical orbitals associated with the lowest energy states arise from wave functions with zero angular momentum. Orbitals with higher angular momentum develop increasingly intricate geometries. All of these patterns emerge because rotational symmetry imposes strict constraints on the solutions of the Schrödinger equation. As physicists explored these connections further, symmetry became an increasingly powerful tool for understanding atomic behavior. One of the scientists who played a key role in this development was the Hungarian-American physicist Eugene Wigner. During the 1930s, Wigner introduced the use of group theory to analyze quantum systems. Group theory is a branch of mathematics that studies symmetries in a highly systematic way. A mathematical group describes a set of transformations that can be combined with one another, while preserving certain properties. Although group theory had originally been developed by mathematicians studying abstract algebra, Wigner realized that it provided exactly the language needed to classify quantum states. In atomic physics, electrons occupy states characterized by specific symmetry properties. Group theory allows physicists to identify how these states transform under rotations and other symmetry operations. Using this approach, Wigner and his colleagues were able to classify atomic energy levels and predict patterns in atomic spectra. Spectral lines, the narrow bands of light emitted or absorbed by atoms, are not random. They follow precise rules determined by the symmetries of the atomic system. These rules are known as selection rules. Selection rules determine which transitions between quantum states are allowed and which are forbidden. When an electron moves from one energy level to another, the transition must obey certain symmetry constraints. For example, the angular momentum of the electron cannot change arbitrarily. Transitions that violate the required symmetry conditions are strongly suppressed or do not occur at all. As a result, the patterns of spectral lines observed in laboratories and astronomical observations reflect the underlying symmetries of atomic structure. Another mathematician who explored the deep connection between symmetry and quantum physics was Hermann Weyl. Weyl was both a mathematician and a theoretical physicist, and his work helped bridge the gap between abstract mathematics and physical theory. During the 1920s and 1930s, Weyl developed sophisticated mathematical frameworks describing symmetry in quantum systems. His work introduced the idea that certain physical properties arise from deeper geometric structures embedded within the equations of physics. Weyl's investigations helped establish the modern understanding that symmetry is not merely a convenient feature of physical theories. Instead, symmetry is often the guiding principle that determines the form of the laws themselves. This perspective has profound implications. When physicists attempt to discover new physical laws, they frequently begin by identifying the symmetries that those laws must respect. The requirement that equations remain unchanged under certain transformations can drastically narrow the range of possible theories. In atomic physics, symmetry determines the allowed quantum states, the structure of orbitals, the patterns of spectral lines, and the rules governing atomic transitions. Even the classification of particles in modern particle physics relies heavily on symmetry groups that extend the ideas first applied to atomic systems. Although the mathematics behind these ideas can become quite sophisticated, the central message is surprisingly simple. Nature appears to be deeply structured by patterns of symmetry. Atoms behave the way they do not only because of forces and energies, but also because the mathematical symmetries of space impose strict rules on what is possible. The shapes of orbitals, the conservation of angular momentum, and the allowed transitions between energy levels all emerge from these hidden mathematical patterns. What began as an investigation into tiny particles inside atoms gradually revealed something far more elegant. The behavior of matter at the smallest scales is guided by a subtle but powerful mathematical order woven directly into the fabric of the universe itself. By the late 1920s, quantum mechanics had already transformed the understanding of atoms. The Schrödinger equation described how electron waves behaved, and the probabilistic interpretation of the wave function explained why electrons appeared as diffuse clouds rather than particles tracing precise orbits. Yet one important ingredient of modern physics had not yet been fully incorporated into this picture. That ingredient was relativity. Albert Einstein's theory of special relativity, introduced in 1905, had revealed that space and time are intimately connected, and that the behavior of objects changes as their speed approaches the speed of light. For most everyday situations, these effects are tiny and can be ignored. Inside atoms, however, electrons can move extremely fast. In light elements such as hydrogen, the electron moves at a modest fraction of the speed of light, but in heavier elements with large nuclear charge, the inner electrons can reach speeds approaching half the speed of light or even greater fractions. Under those conditions, the classical Schrödinger equation begins to lose accuracy. A more complete theory must account for the principles of relativity. The task of combining quantum mechanics with special relativity was taken up by a young English physicist named Paul Dirac. Dirac was known for his quiet personality and extraordinary mathematical intuition. While working at the University of Cambridge during the late 1920s, he searched for an equation that would describe electrons in a way that was fully consistent with both quantum mechanics and Einstein's relativity. In 1928, Dirac introduced what became known as the Dirac equation. Unlike the Schrödinger equation, which treats time and space somewhat differently, the Dirac equation treats them in a manner consistent with the relativistic structure of spacetime. It describes the behavior of electrons as relativistic quantum particles. One of the most striking features of the Dirac equation is that it naturally includes a property known as spin. Electron spin had already been proposed a few years earlier by George Uhlenbeck and Samuel Gaudsmit to explain certain patterns observed in atomic spectra. Spin is an intrinsic form of angular momentum carried by electrons, independent of any motion through space. The Dirac equation predicted this property automatically, without needing to add it as a separate assumption. But the equation contained an even more surprising implication. When Dirac solved the equation mathematically, he found that it produced two sets of solutions. One set described electrons with positive energy, which matched the particles already known. The other set corresponded to states with negative energy. At first, this result seemed puzzling. Negative energy states did not have an obvious physical interpretation. Dirac proposed that these solutions represented a new type of particle, identical to the electron but carrying the opposite electric charge. This hypothetical particle would have the same mass as the electron but a positive charge instead of a negative one. Dirac had predicted the existence of antimatter. A few years later, in 1932, experimental evidence confirmed this remarkable prediction. The American physicist Carl Anderson, working at the California Institute of Technology, was studying cosmic rays using a cloud chamber placed inside a strong magnetic field. Cosmic rays are high-energy particles that originate from space and occasionally collide with atoms in Earth's atmosphere. When such particles pass through a cloud chamber, they leave visible tracks in the vapor. Anderson observed tracks that curved in a way indicating the presence of a positively charged particle with a mass identical to that of an electron. This particle was named the positron. The discovery of the positron confirmed Dirac's prediction and marked the first observation of antimatter. It also demonstrated the extraordinary predictive power of combining quantum theory with relativity. The existence of antimatter revealed that every type of particle may have a corresponding antiparticle with opposite charge. Beyond predicting new particles, relativistic quantum theory also improved the understanding of atomic structure itself. When electrons move at very high speeds near the nucleus of heavy atoms, relativistic effects alter their behavior in subtle ways. These effects change the energies of electron orbitals slightly, producing small shifts in the wavelengths of spectral lines. Such variations are known as fine structure. Fine structure splitting occurs because the energy of an electron depends not only on its principal quantum level, but also on its angular momentum and spin. Relativistic corrections modify these energy levels, producing closely spaced spectral lines that can be measured with high precision. These delicate features in atomic spectra provided early confirmation that relativistic effects were indeed present within atoms. Another important contributor to the relativistic theory of atoms was the Russian physicist Vladimir Fock. Working in the Soviet Union during the 1920s and 1930s, Fock developed advanced mathematical methods for solving quantum equations in atomic systems. His work helped extend quantum mechanics to more complicated atoms containing multiple electrons. One of his important contributions involved improving the description of electron interactions within atoms, using methods that later became known as the Hartree-Fock approach. These techniques allowed physicists to calculate the structure of complex atoms more accurately by considering how electrons influence one another. Relativistic quantum theory therefore deepened the understanding of atomic behavior in several ways. It revealed that electrons possess intrinsic spin, predicted the existence of antimatter, and explained subtle spectral features observed in high-precision measurements. More broadly, it established an important bridge between atomic physics and particle physics. As scientists explored the implications of Dirac's equation, they began to realize that atoms were not merely collections of electrons orbiting nuclei. Instead, atoms existed within a wider framework of quantum fields and fundamental particles. The same mathematical principles used to describe electrons in atoms also applied to other particles emerging from high-energy experiments. Over time, this connection would lead to the development of quantum field theory and the modern understanding of particle physics. The atom, once thought to be the smallest unit of matter, had become a gateway into an even deeper layer of reality. Within its structure lay clues pointing toward an entire world of particles, antiparticles, and fundamental interactions that shape the universe at its most basic level. When we imagine empty space, it is natural to picture a kind of perfect nothingness, a vast, silent void where nothing exists and nothing happens. In everyday experience, empty space simply appears to be the absence of matter. Yet modern physics reveals that this intuitive picture is incomplete. At the microscopic level described by quantum theory, even the emptiest region of space is not truly empty. Instead, space is filled with fluctuating quantum fields that are constantly active, even when no particles appear to be present. This idea emerges from the framework known as quantum field theory, which extends the principles of quantum mechanics into a deeper description of nature. In this view, particles such as electrons and photons are not independent objects moving through an otherwise empty background. They are excitations of underlying fields that exist everywhere in space. For example, the electromagnetic field permeates the entire universe. Photons arise when this field vibrates in particular ways. Similarly, electrons correspond to excitations of the electron field. Even when these fields are in their lowest possible energy state, they cannot remain perfectly still. Quantum mechanics imposes unavoidable fluctuations due to the uncertainty principle. Energy and time are related by a quantum constraint that can be expressed as the uncertainty in energy multiplied by the uncertainty in time must be greater than or equal to Planck's constant divided by 4 pi. Because of this relationship, the energy of a quantum field cannot remain exactly zero for all time. Instead, tiny fluctuations briefly create and destroy pairs of particles and antiparticles. These fleeting entities are known as virtual particles. Virtual particles do not behave like ordinary particles that travel long distances and leave permanent tracks in detectors. Instead, they exist for extremely short intervals of time before annihilating one another. Yet despite their brief existence, their effects can influence measurable physical phenomena. One of the earliest experimental hints of these quantum fluctuations appeared in an experiment involving the hydrogen atom. In 1947, the American physicist Willis Lamb conducted highly precise measurements of the energy levels of hydrogen using microwave spectroscopy. Lamb and his colleague Robert Rutherford were working at Columbia University when they noticed something unusual. According to the predictions of the Dirac equation, certain energy levels in hydrogen should have been exactly equal. Specifically, two states known as the 2s1/2 state and the 2p1/2 state were expected to share identical energy. But Lamb's measurements revealed a tiny difference between them. This discrepancy became known as the Lamb shift. The effect was extremely small, corresponding to an energy difference equivalent to a few thousand millionths of an electron volt. Yet the measurements were clear and repeatable. Theoretical physics needed an explanation. That explanation emerged through the development of a theory called quantum electrodynamics. Quantum electrodynamics, often abbreviated as QED, is the quantum field theory describing the interaction between charged particles and the electromagnetic field. It combines quantum mechanics, special relativity, and the concept of quantized fields into a unified framework. 3 physicists played particularly important roles in developing this theory during the late 1940s. Julian Schwinger in the United States, Richard Feynman at Cornell University, and later the California Institute of Technology, and Shinichiro Tomonaga in Japan. Working independently, each of them developed mathematical techniques capable of describing how electrons interact with the fluctuating electromagnetic field. Their calculations showed that electrons inside atoms are constantly interacting with virtual photons that appear and disappear in the quantum vacuum. These interactions slightly modify the energy levels of the electron. In effect, the electron is not moving through empty space, but through a restless sea of fluctuating fields. The Lamb shift arises because these vacuum fluctuations alter the electron's motion in a subtle but measurable way. Quantum electrodynamics proved extraordinarily successful. Its predictions matched experimental results with astonishing precision. In some cases, theoretical calculations agree with measurements to more than 10 decimal places, making QED one of the most accurate scientific theories ever developed. The quantum vacuum produces other observable effects as well. One of the most striking examples is known as the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir predicted that two uncharged metal plates placed extremely close together in a vacuum would experience a tiny attractive force. This force would arise not from any conventional electromagnetic interaction, but from the properties of the quantum vacuum itself. The explanation relies on the behavior of vacuum fluctuations between the plates. Quantum fields inside the narrow gap between the plates can support only certain wavelengths of fluctuation, while the surrounding space allows a broader range of fluctuations. Because the allowed modes differ inside and outside the gap, the pressure exerted by vacuum fluctuations becomes slightly stronger on the outer sides of the plates than between them. The result is a small net force pushing the plates together. Although the force is extremely weak, it has been measured experimentally using delicate instrumentation capable of detecting forces smaller than the weight of a grain of dust. The Casimir effect demonstrates that the vacuum possesses physical properties. Even in the absence of ordinary particles, the quantum fields that fill space continue to influence the behavior of matter. These insights reveal that atoms exist within a much richer environment than previously imagined. Electrons orbiting atomic nuclei are not isolated from the rest of the universe. They are embedded within a dynamic background of fluctuating fields that subtly influence their motion and energy. What appears to be empty space is actually a stage filled with restless activity. Atomic physics, therefore, leads naturally into deeper questions about the structure of the quantum vacuum itself. Understanding how particles interact with vacuum fluctuations has become an essential part of modern theoretical physics. It connects atomic phenomena to high-energy particle physics, cosmology, and the fundamental forces that govern the universe. The atom, once thought to be a simple object consisting of electrons orbiting a nucleus, now appears as part of a far larger and more intricate quantum landscape. Even the emptiest regions of space participate in shaping the behavior of matter. Up to this point, atoms have mostly been described in relatively calm conditions, the sort of environments that exist in laboratories on Earth. Temperatures are moderate, pressures are manageable, and atoms have the luxury of keeping most of their electrons neatly arranged in orbitals around their nuclei. The universe, however, does not always provide such gentle circumstances. Across space, atoms regularly find themselves in environments far more extreme than anything encountered on our planet. Temperatures can rise to millions of degrees. Pressures can crush matter to densities unimaginable in everyday life. Under these conditions, the behavior of atoms changes dramatically. One of the most important transformations occurs when temperature rises high enough to disrupt the structure of atoms themselves. As temperature increases, particles move faster. In gases, higher temperatures mean that atoms and molecules collide with greater energy. If those collisions become energetic enough, electrons can be knocked completely free from their parent atoms. When this happens, the gas no longer consists of neutral atoms. Instead, it becomes a mixture of positively charged ions and free electrons. This state of matter is known as plasma. Plasma is sometimes called the fourth state of matter, alongside solids, liquids, and ordinary gases. Unlike a typical gas, plasma conducts electricity and responds strongly to magnetic fields because its charged particles can move independently. Remarkably, plasma is the most common state of ordinary matter in the visible universe. The glowing interiors of stars are composed almost entirely of plasma. Lightning in Earth's atmosphere briefly creates plasma channels through the air. Even the faint auroras near the polar regions of our planet arise from plasma interactions between charged particles and Earth's magnetic field. Understanding how atoms behave in these hot environments became a major challenge during the early 20th century, especially for scientists trying to interpret the light emitted by stars. Stars produce enormous amounts of radiation across many wavelengths, and when this light is spread into a spectrum using a prism or diffraction grating, it reveals a rich pattern of dark and bright lines. These lines correspond to atomic transitions occurring within the hot gases of stellar atmospheres. Interpreting those spectral lines requires understanding how atoms behave when subjected to extremely high temperatures. One of the scientists who made a crucial breakthrough in this area was the Indian astrophysicist Meghnad Saha. In the early 1920s, Saha developed a theory explaining how the ionization of atoms depends on temperature and pressure. Ionization refers to the process by which atoms lose one or more electrons and become charged ions. Saha derived an equation that describes the balance between neutral atoms and ionized atoms in a hot gas. Expressed in words, the basic idea behind the Saha ionization equation can be summarized as the ratio of ionized atoms to neutral atoms depends on temperature, electron density, and the ionization energy of the atom. Although the mathematical form of the equation involves several physical constants, its conceptual meaning is straightforward. At higher temperatures, atoms are more likely to lose electrons. At lower temperatures, electrons are more likely to remain bound. This relationship allowed astronomers to determine which types of atoms and ions should appear in the atmospheres of stars at different temperatures. Saha's work transformed astrophysics by providing a direct connection between atomic physics and the behavior of stars. Another important advance came from the work of Cecilia Payne, later known as Cecilia Payne-Gaposchkin. In 1925, while completing her doctoral research at Harvard College Observatory, Payne applied the principles of atomic spectroscopy and Saha's ionization theory to stellar spectra. At the time, many astronomers believed that the chemical composition of stars was similar to that of Earth. Elements such as iron and oxygen were thought to dominate stellar matter. But Payne's analysis revealed something astonishing. When she carefully examined the spectral lines in starlight and accounted for temperature-dependent ionization, she concluded that stars are composed primarily of hydrogen, with helium as the second most abundant element. In other words, the overwhelming majority of the visible universe consists of the simplest atoms. Although Payne's conclusion was initially met with skepticism, later work confirmed that she was correct. Today, it is well established that hydrogen makes up roughly 3/4 of the ordinary matter in the cosmos, with helium accounting for most of the remainder. This discovery was possible because atomic physics provides a kind of cosmic fingerprinting system. Each element produces a unique set of spectral lines when its electrons move between energy levels. By observing these patterns in the light from distant objects, scientists can identify the elements present even across vast distances of space. Spectroscopy therefore acts as a bridge between laboratory experiments and astronomical observation. When astronomers analyze the light from a star, they are effectively studying the atomic transitions occurring in its atmosphere. The same physical laws governing atoms in laboratories on Earth apply equally to atoms in distant galaxies. This remarkable universality allows scientists to infer the temperature, chemical composition, and even motion of astronomical objects simply by studying their light. In the most extreme environments, such as the interiors of massive stars or the vicinity of neutron stars, atomic structure can be altered even further. Intense gravitational fields, enormous pressures, and powerful magnetic fields can reshape the behavior of matter in ways that continue to challenge theoretical understanding. Yet the foundation of these investigations always returns to atomic physics. The spectral lines that reveal the composition of stars arise from electrons transitioning between quantum states. The ionization of atoms in stellar atmospheres follows statistical rules derived from quantum mechanics and thermodynamics. From the smallest atomic transitions to the largest stellar systems, the same underlying principles apply. Atoms, governed by quantum laws, become the tools through which humanity reads the physical story written across the universe. For most of human history, atoms were far beyond direct human control. Scientists could infer their existence, measure their properties, and build theories describing their behavior, but the idea of manipulating individual atoms once seemed almost unimaginable. Yet during the late 20th century, advances in experimental physics began turning that idea into reality. Researchers developed techniques capable of slowing atoms down, trapping them in place, and studying them one at a time. Instead of observing enormous collections of particles behaving statistically, physicists could now isolate single atoms and watch their quantum behavior unfold. The key to achieving this extraordinary level of control came from an unexpected source: light. Light carries momentum as well as energy. When a photon strikes an atom and is absorbed, it transfers a tiny push to the atom. Under ordinary circumstances, this effect is far too small to notice. But if carefully arranged, repeated interactions between atoms and light can dramatically alter atomic motion. This principle became the foundation of a technique known as laser cooling. During the 1980s, several groups of researchers began developing methods to slow atoms using precisely tuned laser beams. Among the scientists who played leading roles in this work were Stephen Chu, Claude Cohen-Tanuji, and William Daniel Phillips. Their experiments demonstrated that carefully tuned laser light could reduce the motion of atoms to extremely low speeds. By directing laser beams at atoms from multiple directions, the photons exert forces that oppose the atom's motion. Whenever an atom moves toward a laser beam, the frequency of the light appears slightly shifted due to the Doppler effect. By tuning the laser frequency just below the natural absorption frequency of the atom, scientists ensure that atoms moving toward the beam absorb photons more readily than those moving away. Each absorbed photon slows the atom slightly. After absorbing the photon, the atom eventually emits light in a random direction, producing a small recoil. Over many absorption and emission cycles, the net effect is a gradual reduction in the atom's motion. This process cools the atoms to temperatures astonishingly close to absolute zero. Absolute zero is the temperature at which thermal motion would theoretically cease. On the Kelvin scale, absolute zero corresponds to 0 Kelvin, or approximately minus 273 degrees Celsius. Using laser cooling, scientists can routinely achieve temperatures only millionths or even billionths of a degree above absolute zero. At such low temperatures, atomic motion slows dramatically. Atoms move so slowly that they can be confined using electromagnetic fields and beams of light. One common method for trapping atoms uses a configuration called a magneto-optical trap. In this device, magnetic fields and laser beams work together to hold atoms in a small region of space. The combined forces create an invisible cage where atoms hover almost motionless. Another approach uses optical traps, sometimes called optical tweezers. These traps rely on extremely focused laser beams that create regions of high electromagnetic intensity. The electric field of the light interacts with the atom's internal structure, producing forces that draw the atom toward the center of the beam. In effect, the atom becomes suspended within a tiny well of light. These tools allow physicists to hold and manipulate individual atoms with extraordinary precision. The ability to control atoms so carefully opened new possibilities for studying quantum systems. Instead of examining the averaged behavior of enormous numbers of particles, researchers could now investigate the properties of single atoms and their interactions with photons. Two scientists who made important contributions in this area were Serge Haroche in France and David Wineland in the United States. Serge Haroche conducted experiments that explored how single atoms interact with individual photons inside specially designed electromagnetic cavities. By trapping photons between mirrors and allowing atoms to pass through the cavity, Haroche's experiments revealed delicate aspects of quantum measurement and the transition between quantum and classical behavior. David Wineland pursued a related approach using electrically charged atoms known as ions. By trapping individual ions using electromagnetic fields, Wineland's group could manipulate their quantum states with extraordinary accuracy. These trapped ions could be cooled, controlled with lasers, and made to interact with one another in precisely defined ways. Such systems became powerful platforms for exploring quantum information. In conventional computers, information is stored in bits that can take on values of 0 or 1. Quantum systems allow a more flexible form of information storage using quantum bits, or qubits. A qubit can exist in a superposition of states, meaning it can simultaneously represent combinations of 0 and 1 until measured. Atoms and ions provide natural candidates for qubits because their quantum states can be precisely controlled using electromagnetic fields and laser pulses. By manipulating these states and entangling multiple atoms together, researchers can perform operations that form the basis of quantum computation. Although practical large-scale quantum computers remain an active area of research, experimental systems using trapped ions, neutral atoms, and superconducting circuits have already demonstrated many essential quantum algorithms. Beyond computing, the ability to control atoms has enabled remarkable advances in measurement science. Atomic clocks, for example, measure time by monitoring extremely precise transitions between quantum states of atoms such as cesium or ytterbium. These clocks can keep time so accurately that they would lose less than a second over billions of years. Such precision plays a crucial role in technologies like global positioning systems, where extremely accurate timing signals allow satellites and receivers to calculate positions on Earth. The capacity to manipulate atoms also supports research in quantum simulation, where controlled atomic systems are used to model complex materials and physical processes that would otherwise be difficult to study. In laboratories around the world, arrays of individually trapped atoms now act as miniature quantum laboratories, allowing scientists to explore the frontiers of physics one particle at a time. What began as an effort to understand the structure of atoms has evolved into the ability to shape and guide their behavior with extraordinary delicacy. Atoms, once hidden far beyond the reach of human senses, have become tools through which humanity explores the quantum foundations of reality. Even after more than a century of extraordinary progress, the physics governing atoms still contains deep mysteries. Quantum mechanics provides a framework that predicts experimental results with astonishing accuracy, yet the theory also raises questions that remain unresolved. Physicists can calculate the energy levels of atoms with remarkable precision. They can predict spectral lines, chemical bonding, and the behavior of electrons in complex materials. Quantum electrodynamics, the theory describing interactions between charged particles and light, produces predictions that match experiments to more than 10 decimal places. And yet, beneath this impressive success lies a conceptual puzzle. Quantum mechanics describes nature using probabilities rather than certainties. The wave function provides a mathematical description of possible outcomes, but it does not specify which outcome will occur in a particular experiment. When a measurement takes place, the wave function appears to collapse suddenly into a single result. Before measurement, an electron may exist in a superposition of possible states. After measurement, it appears in one definite state. Why this happens remains one of the most debated questions in physics. Some physicists accept the probabilistic interpretation as a fundamental feature of nature. Others have wondered whether hidden mechanisms might exist beneath the theory, determining outcomes in ways that are simply not visible to current experiments. This possibility became the focus of a profound theoretical investigation by the Northern Irish physicist John Bell. In 1964, Bell developed a mathematical argument known as Bell's theorem. His work addressed a question originally raised decades earlier by Albert Einstein, Boris Podolsky, and Nathan Rosen. Einstein and his colleagues had been troubled by the strange predictions of quantum mechanics, particularly the phenomenon known as quantum entanglement. Entanglement occurs when two particles interact in such a way that their quantum states become linked. Afterward, measuring the state of one particle instantly determines the state of the other, even if the particles are separated by large distances. Einstein famously described this phenomenon as what he called spooky action at a distance. He suspected that the apparent randomness of quantum mechanics might conceal deeper hidden variables that determined the outcomes of measurements. Bell's theorem tested this possibility. Bell showed that if hidden variables existed that preserved both realism and locality, meaning that physical properties existed before measurement and that no influence travelled faster than light, then certain statistical correlations between entangled particles would obey strict mathematical limits. Experiments could test whether those limits were respected. When physicists later performed these experiments, the results were astonishing. Beginning in the early 1980s, the French physicist Alain Aspect and his colleagues conducted a series of experiments measuring correlations between entangled photons. These experiments were designed to test Bell's inequalities, the mathematical constraints derived from Bell's theorem. The results consistently violated those inequalities. In other words, the behavior of entangled particles could not be explained by any theory that relied on simple hidden variables obeying local cause and effect. Quantum mechanics appeared to be correct. Entangled particles behave as if they share a single quantum state, even when separated by large distances. The correlations between their measurements emerge instantaneously, although they cannot be used to transmit information faster than light. This phenomenon remains one of the most fascinating aspects of quantum theory. Different interpretations attempt to explain what it means. One alternative interpretation was proposed by the physicist David Bohm in the 1950s. Bohm developed what is known as the pilot wave theory, also called Bohmian mechanics. In this framework, particles possess definite positions at all times, guided by a hidden wave that determines their motion. The wave function still plays a central role, but the randomness of measurement outcomes arises from our ignorance of the underlying particle positions. Bohm's interpretation reproduces the predictions of standard quantum mechanics, yet it introduces non-local connections between particles in order to account for entanglement. Other interpretations take different approaches. The Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg, treats the wave function as a complete description of physical reality, but emphasizes the role of measurement in determining outcomes. The many-worlds interpretation, proposed by Hugh Everett in the 1950s, suggests that every possible outcome of a quantum event occurs in a branching set of parallel universes. Each interpretation offers a different philosophical perspective, yet all produce the same experimental predictions. Despite decades of debate, no single interpretation has achieved universal agreement among physicists. While these conceptual discussions continue, experimental research into atomic and quantum systems has advanced rapidly. Around the world, laboratories explore quantum phenomena with extraordinary precision. Institutions such as the European Organization for Nuclear Research, commonly known as CERN, investigate the fundamental particles and forces that underlie matter. Although CERN is best known for high-energy particle physics, many of its discoveries inform the deeper understanding of atomic structure and the quantum fields from which particles arise. The Max Planck Society in Germany operates numerous research institutes dedicated to quantum optics, atomic physics, and condensed matter science. These laboratories develop advanced techniques for controlling atoms, studying entanglement, and exploring the boundary between quantum and classical physics. Another important centre is the Perimeter Institute for Theoretical Physics in Canada, where researchers investigate foundational questions about quantum mechanics, space-time, and the structure of physical law. Experiments continue to push the limits of measurement and control. Scientists can now entangle large numbers of particles, manipulate individual atoms with laser precision, and measure tiny energy shifts caused by quantum fluctuations. These experiments test the predictions of quantum theory in increasingly demanding ways. At the same time, new theoretical ideas attempt to connect quantum mechanics with gravity, the one fundamental force not yet fully incorporated into the quantum framework. Approaches such as loop quantum gravity and string theory aim to describe how spacetime itself might behave at the smallest scales. The atoms that once seemed like the ultimate building blocks of matter have become part of an even larger story. They are governed by quantum laws that continue to challenge intuition and inspire investigation. Each new experiment reveals additional layers of complexity, while each new theory attempts to uncover deeper patterns hidden within the mathematics of nature. The study of atoms therefore remains far from complete. Instead, it stands at the frontier of a continuing journey, one that seeks to understand the fundamental structure of reality itself.